Okay, so we'll start from where we left off last time. I think we started with chapter 3, so the half-wave rectifier chapter. So we said that this is the first of the AC to DC converters. So we're covering one of the quadrants of our triangle here, of our square here. So next, after this, we will do the AC to AC converters, and then we will do the DC to DC, and then we'll do the DC to AC converters. That's the current plan. So anyway, so we started looking at the simple half-wave rectifier. It's something you've seen in 325 before, so we skimmed through it pretty quickly. Let's look at we'll look at the waveforms quickly again. So we have input source, output load, which is resistive, and your input is a sinusoidal waveform that looks like this. This is V input, this is V input, and we would like to see what V output looks like. So what does V output look like? Sure. So again, you treat each of these points as a DC value, right? So if you put a DC source here and a diode and a resistor, obviously the potential here will be higher than the potential here. So this is the highest potential in the circuit. This diode will see a potential on this side that is higher than this side and will start conducting. So during the positive half cycle, it will start. So anytime these values are positive, this diode will start conducting. What happens at pi? At pi, again, this is a resistive load. Since it's a resistive load, then the current, so this is the input voltage, then current flowing in this circuit, I, will also look the same as the voltage but scaled down with the value of the resistor R. So it's the same sinusoid, same frequency, same everything, but has a peak value of V over R. Right? So that's the current waveform. What happens at pi? At pi, the current tries to go negative. Right? It is trying to go negative since the voltage is going negative, and this is a resistive load. So again, the circuit looks like this when the diode is on, right? This is how the circuit looks like when the diode is on. You apply a voltage here, V input, and this V input will equal the V output exactly, and hence the current is V output, or V input is V input divided by R, right? So at pi, since the voltage tries to go negative, the current will also try to go negative. As soon as the current tries to go negative, what happens? This diode stops conducting. The diode will stop conducting if the potential here is higher, or you're driving current in the opposite direction. These are the conditions for the diode to stop conducting, right? So you are trying to drive it with negative current. You're trying to push current in the opposite direction, so it will stop conducting. So the current will look like this in the positive half cycle, and then 0. So what does the output voltage look like? The output voltage looks exactly like the input voltage. So this is V input, this is V output. It has a peak value also of V input in the positive half cycle. In the negative half cycle, it is 0. Since there is no current flowing and there is no voltage across this resistor, so the output voltage is 0. What is the voltage across the diode? So if we assume that the polarity of VD, or polarity of voltage across the diode VD, is in this direction, it's the same as the input? Exactly. So it's when it's conducting, it's ideally 0, right? And then it's the same as the input, so it's negative here, and it will have a peak value of negative Vm max, like this one, minus Vm. Okay, so that's this case. How about a more complicated case? Let's remove this resistor and add an inductor and see what will change, right? So actually, before we do that, so what changed between V input and V output? What happened to my output voltage? Here, what was the average value of this output of the input voltage? Yeah, here the average value of the input was equal to 0. Here, the output voltage has an average value, right? There's no negative area. So since it has an average value, then I've created DC. So I've converted AC to DC, right? So I've converted something with a 0. AC is something with 0 average value. That's AC. This is something with an average value. So it has a DC component, right? So this is something that has a DC component. Can I control the value of DC component? If I have a DC motor, this DC motor, I would like to control its speed. How do you control the speed of a DC motor? You just change the value of voltage, right? If you change the value of voltage, you will change the value of current, and you will change the torque, right? So that's for a DC motor. So is this something, can I control the average value of the output voltage? Yeah, if I control VI, but VI here is coming from a fixed source, so I cannot control the output really. I just have a fixed value of output voltage, right? So this is the limitation of this converter. Also, we said that the output current looks like this red waveform, right? And of course, the output current is also the input current, correct? And output, since it's just it's a series loop, right? So output current is equal to the input current, same. So what is one of the limiting features, or one of the features of this output current, of the input current and the output current, is that it also has an average value, right? So it's a DC value. Can you put DC through a transformer? You cannot push DC through a transformer. So this cannot be a circuit to convert AC to DC if you're going to try to step down the voltage using a transformer at the front end, because transformers will not allow you to push DC current through them. If you try to push DC current through the transformer, you will not be able to generate the back EMF voltage across you will not be able to generate voltage across the windings. You know, transformer is nothing but what? Windings, right? These windings, here you put a voltage on this side, current starts flowing, you know, in the core, this AC current is going to be generating AC flux. Time-varying current will generate time-varying flux. This time-varying flux will generate a voltage across each of these turns will have a voltage across it, and hence you will have a voltage across the full winding of the transformer, primary and secondary. Right? If you don't create this voltage, then this is like a piece of wire. Right? The transformer, you don't have E in here. You don't have E equals ND phi by dt. You put a voltage here, and you have a piece of wire that you've wrapped here. But if transformer action is happening, as soon as you have time-varying flux, you generate a voltage across the primary, and you also generate a voltage across the secondary, because the same flux, same time-varying flux, is linking the primary turns and secondary turns. So the same value of voltage, theoretically speaking, per turn, is created across the transformer turns, and then depending on the number of turns, you have a certain voltage on the primary and secondary. Because you have a voltage opposing your input voltage, then the current flowing in the transformer is not infinite. You have a voltage here at the input and a voltage across the windings. So the difference in voltage will cause current to flow, right? And this current will depend, of course, on the load that you put. But if you do not have time-varying flux, if you have a DC, then you don't have this E developed. Then you just have a short circuit. You just have a piece of wire. It's not a transformer, just a piece of wire. Make as many turns as you want. It does not really matter, right? Just because you have turns and a core doesn't mean you have a transformer, right? Because you have time-varying flux, then you have a transformer, right? So then, because I have DC here now, then I cannot push this to a transformer. So let's say I want this is 120 volts, and I want a DC motor like 5 volts, to run a 5 volt DC motor. One good way to do it would be, okay, take this 120 volt through a transformer. One cheap way to do it would be 120 volt through a transformer. So here we have 120, for example, and here I have a certain number of turns. Here I have a certain number of turns to bring down the voltage from 120 to, let's say, 7 volts or 8 volts or 6 volts or whatever. It's close enough. If you put 6 volts on a 5 volt motor, it's not going to burn, right? But you choose the ratio of turns such that you have the ratio of voltage close to what you want, right? Then you put your load here, and then you put your diode rectifier here. Sorry, I'll draw a diode rectifier as a block here. This is your AC to DC rectifier, and then you put your DC motor, right? This is a simple circuit, a simple way to run a 5 volt or 6 volt motor using your high voltage AC supply, right? But this AC to DC rectifier cannot be this half wave rectifier that we just showed. It cannot be. This is not what's in this box. Why? Because then the current flowing through this transformer will be DC. Then you will burn this transformer, right? It's useless. So one of the limitations of this, so it's a very simple circuit, very nice, very simple, very elegant, nicely you can use it. It converts from AC to DC, uncontrolled output. Fine, that's fine. That's a characteristic of many diode circuits because you cannot control a diode. Really, it's controlled by the external environment or external circuit, but you cannot use it after a transformer because of the way the current shape looks like. So, but it produces an average value. So the average value of this waveform is equal to what? 1 over the period. The period is 1 over 2 pi. The what? V of t, which is V max sine omega t in this case, which was my input, d omega t. The average value of this is V max over pi. Right? We're good? So now let's go to the more complicated case, where I have a circuit with a diode and a resistor and an inductor. So this is my V input, this is my diode, this is my R, this is my L. My output voltage is here. And then I'd like to do the same thing, draw the waveforms. So this is plus minus VD. Okay, so now what? This is my input voltage. What does my output voltage look like? RL together. Output is this. What does the current look like first? Let's make it easier. What does the current look like? Okay. How is this circuit going to look? What will this circuit look like when the diode is on?
Okay, so it's in the
When the diode is on, this diode will look like a short circuit, correct? So I have my source, and I have my RL load. This you've seen many times in 214, correct? So what will the current look like here? It's the first order differential equation, natural response, forced response. Natural response comes from the fact that I have energy stored in the inductor. If I have, here I will assume I don't have. And then the forced response will be equal to what? The voltage divided by the impedance. You remember? Remember that from 214? So just the voltage, AC voltage, divided by the impedance. It's AC, right? It's a voltage with a magnitude and an angle divided by an impedance, magnitude and an angle. Just, the magnitude of the voltage with its angle and divided by the magnitude of the impedance with its angle, whatever that is, right? So that's the forced response of the circuit. And that's what I see here. Assuming I don't have a natural response, meaning I don't have an initial condition for current, and this is the solution. I is equal to this. This is what? This is what? It's a linear circuit, so it will behave like what? It will also provide a linear response. It will always provide, so there will be no discontinuities to the current. But what does an inductor typically do to the current waveform? V equals, if I only have a pure inductor, it resists instantaneous changes in current, right? VL is equal to L di by dt, so I of L is equal to 1 over L integral of VL dt. If I have a pure inductor, this is not pure inductor, okay? If I have a pure inductor, what will the current look like? This is sinusoid. So what's the integration of a sine? Integration of a sine is not a cosine. Negative cosine, right? So it will be something that is negative cosine. Cosine will be here. So this will be something that look like this. You agree? That's if I have a pure inductor. I don't have a pure inductor here, of course. Right? So since I don't have a pure inductor, we get the effect of the exponential, ae to the minus t over tau solution of the differential of the first order differential equation. So what's going to happen is current will rise exponentially. When will it rise? Now here, when is this die going to start conducting? Assuming this L is very small. Okay, let's assume this L is very, very small. If this L is very, very small, then it looks like a resistor, right? What did we say the resistor would do in this case? As soon as I have a positive voltage, I will have a positive current equal to the voltage divided by the value of the resistance, right? So, and so on and so forth, I will get a current that looks like this. And at this point, current will stop flowing because I'm trying to push current in the opposite direction through the diode. That's what we said in the previous case. Now what's going to happen? Now we added small value of inductance. What does an inductor do? Inductors resist the change in current, right? So here I have a current that was supposed to rise this fast. It's gonna slow it down. It's gonna slow it. It will rise exponentially. Instead of rising with a sine or a cosine, because for a pure inductor case, it will rise exponentially according to the ae to the minus t part of the equation. We will derive the equations next. But I just want you to okay. What will an inductor do? Inductor is like, you know, those water wheels. You know, let's say you have a channel of water and you put this water wheel in there. This water wheel has these, small, divided into these sections, right? Each section you fill it with water, and what does it do? It moves this water to the other side, moves the water to the other side. So instantaneously, if I have input, am I going to have output? At the very beginning, I will not have output. I will not have output. But now in steady state, if I make a big change in input, am I going to see a change in the output? Steady state. It will not change instantaneously, but you will see it after a while, right? So inductors is the same thing for the current. Inductors do the same thing for the current. You will see the effect of the current changing at the input, but it will take a while, right? So you will have, current will start flowing when, at the same time, the diode starts conducting. When does the diode start conducting? As soon as the voltage here becomes positive. The voltage here becomes more positive than this node. So it's definitely more positive than this node, since this is now the most positive potential in the circuit, right? This is the most positive potential in the circuit is now here. So this node is definitely at a higher potential than here. So the diode will start conducting. The circuit looks like this. As soon as the circuit starts looking like this, I will have to solve my equation. I of t is equal to my force response and my natural response. It will be the sum of the force and natural responses together. And we will look at the equations, but physically what's going to happen is, okay, instead of being able to rise fast, it's going to slow down the current, the rise of the current. Do we agree? It will slow down the rise of the current. But the current will then rise. So it will slow down. This slow down is an exponential rise in the current. Okay? And what did we say happens at the end? If now at the resistive load case, the current will go down to this point and try to go negative. Right? As soon as it tries to go negative, the diode will block. How about in the inductor case? In the inductor case, exactly. So when does inductor current become negative? If the voltage is negative, I mean, this is an integration, right? So if the integration before was a huge positive value, and now you add a small negative value, is the integration, because the integration is what? Initial condition plus integral. Initial condition plus integral. Initial condition plus integral. Now I have a big positive value from before, and now I added a small negative to it. Is it instantaneously going to become negative? No. So the voltage will, so the current, sorry, the current will not instantaneously become negative as soon as the voltage becomes negative. It will not. But what's going to happen to it? You had a positive value, now you added a small negative value, a small negative value, a small negative value. What does that mean? What does that do? Keep decreasing the current. Right? So you have a positive area, then you keep adding negative areas to it, then at some point you will have zero. Right? So that's what's happening. So now at this point, my voltage started to become negative. But I'm also exaggerating a little because it's a voltage across the actual inductor I'm talking about. Here I'm talking about the voltage of the combination, but bear with me, we'll draw the inductor voltage now shortly. Yes, sir.
Well, you don't want that. You don't want it to become negative, right? Or
But as soon as
you want it to become
what
negative,
becomes
so
what
you have an average current.
what will become negative? What don't I want to become negative?
The current.
The current cannot become negative. We have to agree to that. As soon as it starts to become negative, the diode will block it. You don't have that choice. It's not a luxury. But the voltage can become negative. For the resistive load case, as soon as the voltage became negative, what happened? The current became negative because I is equal to V equals IR. Exactly, right? V equals IR for the resistive case. If the voltage becomes negative, the current is negative. The current is negative, voltage is negative at the same time, right? But for the inductive case, that's not the case. I mean, that's not the story now, right? I have a V output here. V output is equal to VR plus VL, right? What is VR? What is VL? VR is IR, that's fine. But VL is L di by dt, right? So V output is not as soon as V output becomes negative will I have current becoming negative. And it's again, what did we say the inductor does? It delays the current, right? So you will see the same effect that was supposed to happen, but in a delayed fashion. So now, current for the resistive load case, current started to rise at zero, sinusoidally, very fast, right? Because I didn't draw sinusoidally very nice, but remember, sine wave. Actually, what is sine 30 or sine 15? Sine waves rise very fast, but then they start, slowing down after 45 degrees, between 45 to 135. The change is not too much, but from 0 to 15, big change in the value of the sine, or big change in the value of the sine, right? But I didn't draw it nicely here. But so anyway, so the sine or cosine was rising very fast for the resistive case. For the inductive case, it slowed down, but it started rising at the same point. How about for the inductive case here?
So it does not die.
What do you mean? So, no, the diode is there, but it's on now. It's on. What's going to happen? Current will start decreasing when what happens? When the inductor voltage becomes negative. What is the inductor voltage equal to? The inductor voltage is equal to what? VL is equal to V output minus VR, right? So, or actually it's V, so this is the input voltage, this is VR, and this is VL, right? So V input is equal to VR plus VL, right? So VL is equal to V input minus VR, right? So what does VR look like? VR, what does VR look like? I times, so it's the current multiplied by the value of the resistance. So it's going to also rise slowly, right? This is VR. What does VL, what's the voltage across the inductor look like? Let's do it slowly. Yeah, what does the voltage across the inductor look like? V input minus VR, right? So input voltage and VR are the same initially, right? So it's 0 here. How about what is happening to VR? VR is increasing. VR is increasing. At the beginning, V input is increasing, right? They're both increasing. And then what happens? At some point, V input starts to decrease, Right? The input is starting to decrease while VR is delayed. Remember, this is the VR takes the same shape as the current, and the current is delayed with respect to the voltage. So fine, the VR will start decreasing at some point, but it will be delayed with respect to the input. So the input will start going down, but VR will start, you still keep rising a little bit, until there's this inequality taking place. And then at some point, what happens? At some point, VR is equal to V input, for example. And at that point, VL starts to become negative. So the difference between them is initially what? Initially positive. V input is definitely higher initially, right? V input minus VR. VR is very small. It rises slowly because the current rises slowly. V input rises fast. So the difference V input minus VR is initially positive, right? And then at some point it becomes zero. They become equal to each other. And then what happens? Then what happens? The current, if the resistive load case, the current was falling here. As soon as voltage became negative, current became negative. What do you expect the inductive load case would do? Would it fall at the same point? Would it fall before? Would it fall after? After, because it's always delayed. For the inductive load current is always delayed with respect to the resistive case. Right? There's always a lag in current when you have an inductive load case. So the current will fall definitely somewhere after the resistive load case fell. Right? So the case with the resistor stopped here. Where will the inductor case stop? Some point after. Where after we will calculate based on the equation. I don't know. It depends on the value of inductance. Remember that the differential equation has a time constant R over L. Depending on the time constant, this will either fall here, or fall here, or fall here, or fall here, or whatever, right? So we will calculate that. But it will definitely be beyond the point where the resistor current starts to fall. Try to go negative, right? So the inductive current case, the current will fall to zero at this point here, right? So if this is the current, right? And this is the voltage across I would like to draw the voltage across the inductor. When does the voltage across the inductor equal zero? When this slope is equal to zero, when there's no change in current. Where is that happening? Somewhere here. Right? Somewhere beyond. So it's beyond here, because I know this is the point where there's no change in the input voltage. Right? This is the point where there's no change in the input voltage. But we said that the inductive current lags the resistive case, right? So this starts falling, but the inductor current still keeps rising a little bit beyond this point. A little bit beyond this point, it hits its peak value and then starts to go negative because I start adding negative areas. This integration. The voltage across the inductor starts becoming negative, and I start adding negative areas. So at this point here, my inductor voltage is 0. Right? And then my inductor voltage is what? Negative. It's negative all the way until this point. What happens at this point is that there's a significant abrupt change. I had current flowing, and then now current is 0. So what does this mean? I had current flowing. If you look at the equation, I had current flowing, and then it became 0. It's because of the significant change in this slope. There will be a significant change in voltage. If the slope changed here, I had current. It was current with a value. Then it became 0. Abruptly, it became 0. Stopped. Then you'd expect that the voltage across the inductor would also have a significant change at this point here. Right? So this is the current, and it's also the inductor resistive voltage across the resistor. So they're the same. And this is the voltage across the inductor. And then the sum of these two is the output voltage. Right? So what will the output voltage look like? The output voltage will look obviously like the input voltage when the diode is on. As long as the diode is on, the output voltage will look like the input voltage. Do we agree? So that if I draw the output voltage, then and this is, let's say, my input voltage. Then as long as the diode is on, the output voltage will equal the input voltage. When is the diode off? The diode turns off here, because at this point, what's happening? The current tries to go negative, right? It's a linear circuit. It's a linear circuit. You give it a voltage, it will give you a current. You gave it a voltage that is sinusoidal. This is an RL circuit that will have a response. That's part of it is sinusoidal, part of it is exponential because of the fact that I have a first order differential equation, right? So you will have a current that looks like that's trying to go negative beyond this point. The current tries to go negative. As soon as the current tries to go negative, same thing happens. The diode blocks. The diode blocks, current becomes 0, voltage across the inductor also becomes 0. But my output voltage now looks like this. This is now my output voltage. This area plus this area. Obviously, it has an average value, right? The average value here is not 0. But the average value here is less than the average value for the resistive case, because I've added a negative area here. Yes? No? Maybe so? Yeah? Yes?
You said VL changes abruptly when the current goes negative. Won't it go higher because isn't it proportional to the change in?
Became 0. Current
Yeah.
became 0 afterwards, so the VL will become 0.
Okay.
Right?
Oh, okay. So that jump is just.
The jump is because I went from, having, again, I did not draw this nicely, but if you draw this properly, it will look, it will fall more like this, pretty sharp. It rises slowly, and it will fall this way. So the change in slope, this is the slope, this is di by dt, right? So di by dt had a value here, and then became 0, all of a sudden, right? So I caused a significant change in current in a short period of time. I have current, and then I have 0. So then that's why there's a significant change in voltage here.
So now if I can control the resistance, I can gain more output.
Sure.
Output.
Exactly. If you increase resistance, this area will be smaller. If you increase inductance, this area will be larger. That's what you have. But this is typically not something you control. This is typically your load. Right? Transformer. What was the equivalent circuit for the transformer that Dr. Haytham gave you? It's a RL circuit at the end of the day. The induction motor. What's the equivalent circuit? RL circuit. The power system. What's the equivalent circuit? RL circuit. Everything has an equivalent circuit that looks like an RL. Almost everything. I don't want to say everything. Almost everything has an equivalent circuit that looks like an RL, or an RL with a source. Actually, not every. Heaters look just like a resistor. A heater will look like a resistor. A transformer, a motor will look like an RL if it's an induction motor, for example. But if it's a synchronous machine, it will look like something different. We will do that next. But let's first finish this. But this is applicable for induction motors, for example, and transformers. Simple RL circuit. This is equivalent circuit. You can model it as that. Okay, so everybody's okay with this? How about, yes, sir?
So one question.
Yeah.
Could you go over again how we got the waveform of I output? I know the I input is the integration of the V. So that's why I put an inverted cosine.
But that's for
That's for
pure inductive case. This is not a pure inductor. That's why, for a pure inductive case, yes. But for a non-inductive case, for an RL circuit, you have an RL circuit. How did you used to find the current? The current I of t is equal to, this is a equation that you can solve using Laplace, transform, Laplace transform, and you can solve. This is a voltage source, for example, v of t. You take that as v of s, or in the Fourier domain, you can model that as v of the z transform. You can model it as v of z. But anyway, this will have a current that looks like what? And it will have two components: a natural response and a forced response, right? It's a first order differential equation. What is the this is v of t is equal to what? I of t times r times I of t plus L di of t by dt, right? If I make this left hand 0 and I assume that there's no forced response, this becomes a first order differential equation with, I don't know what it's called, first order differential equation with, when the right hand side is 0, the solution to this looks like what? A e to the minus t over tau is the solution to this first order differential. So I of t, in this case, is the exponential function, where tau is equal to r over L, right? So what is tau? Which I of t are we talking about here? Here I've removed my forced response. I've removed my source. This is only the solution to this part. This is this part of the solution for the current, right? So I of t is equal to I n of t is equal to a e to the minus t over tau. What is I f of t equal to? It's v of t divided by the impedance. R times I of t plus L di by, R plus omega L, right? So this is I force response of omega t, and this is omega t, and then this is R plus omega L, right? So this will be your forced response. It's due to the fact that you have a source, right? So then the full current, the actual current flowing through the circuit is equal to this plus this part. And then you would find A from where? From your initial conditions. What are your initial conditions? I had current equal to 0 at the beginning. So I of 0 is equal to 0 is an initial condition. So again, I will show the equations on the slides, but that's how you would do it here. Canvas like that. So I don't know, did I answer your question?
Yeah.
What was the question? Sorry.
It was how we got the I out.
Okay, so the shape of the waveform.
Yeah.
Okay, the shape of the waveform will be governed by this equation, natural plus forced response. But forget about the shape of the waveform, okay? At the end of the day, this is an inductive circuit. Versus, I try to compare to the resistive circuit so that you always relate them to each other. So what was happening to the resistive circuit current? This was my voltage, and for the resistive case, the current looked exactly like the voltage and then became 0 here. For the inductive case, what is happening to the current? It will be delayed with respect to the resistive case, period. You always know that. Always be delayed with respect to the resistive case, right? It will be limited, or limited in change with respect to the resistive case, right? So here, both circuits start conducting at 0. But the resistive circuit case, the resistive currents, jumped to these values. The inductive current case slowly rises. And always think of that wheel, right? Always think of that wheel. Initially, there's just a pipe versus that wheel, right? This is just like the pipe, water flowing through a pipe, and this is just like water flowing through that wheel, right? It will slowly rise. At some point, it will hit a maximum. Where is this maximum? It will definitely be beyond the maximum of this. The maximum will not happen at the same time because it's delayed with respect to it, right? It's delayed with respect to it. So the maximum of this blue waveform will happen a little bit later, sometime here. It's governed by the values of R and L and the input source, right? And then at some point, it starts flipping, the slope starts to become negative. right? And then when will it cross here? When will it cross my 0? It will cross after the resistive case. Whereafter we will calculate it later using the equation. But it will cross after, depending on the value of R and L. It can never cross before. If L is 0, where is it going to cross? Here. Right? The resistive case. If L is 0, this is where it will cross, the resistive case. If you have an L, then it will be beyond it. How far beyond it? Depends on the value of L. Okay? Yes? No?
So after the conversion, does it reach steady state where the current is always ahead of the?
No, because as soon as it tries to cross 0, then it tries to push current in the opposite direction, the diode blocks, and that's it. I'm done. The circuit starts to it's disconnected now. Okay, so now the third case, which is the third model of equipment that we have in a power system. We said we have R, like heaters, RL, like transformers and induction motors. And then we have the last case, is a source, is a resistor, inductor, and a DC source. This looks like a DC motor or a synchronous motor because these have magnets or they have a external field, right? The field winding. So these things, I mean, a generator or a synchronous motor or a generator or a DC motor, if you just spin the motor, you will have voltage created at the output, right? Why? It's due to the fact that you have magnets or due to the fact that you have a external field applied on the field winding of the synchronous machine, right? So this is the third family of type of equipment we have in a power system that can be modeled as an RL and a source, a DC source. This is it, really. We don't have. These are all electrical equipment can be modeled fine. You can. There's a minority of electrical equipment that can be modeled with a capacitance in the equivalent circuit, but the majority is either R, L, or RL and a source. Okay. So how now will this circuit behave? You want to go through the same process. Again, I have my input voltage. It looks like this. My objective is also to calculate the output voltage. The output voltage is across the full chain here, okay? So this is the full chain. This is V output across the RL and the source. Okay. So what's going to happen? And this is my input DC. This is VDC. So how does this work? Yes, sir.
Can we move the VDC to the left side? Subtract the two sources and treat it as the RL case?
No, but I'm saying that my V output is across the RL and the source. I want to draw V output. You can if you want to do it that way, but how will that help you?
Yeah, so the source current is higher than the DC.
This is a circuit with two sources. Superposition automatically. As soon as you see two sources, you do superposition, right? So you will have a contribution from this source and a contribution to this source. So only when this source is higher than this source will current start flowing, right? Only when this source is higher than this source. So this is happening here at this point. The AC becomes higher than the DC at this point. Right? So what's happening before this point? What's happening before this point?
Just block.
Nothing is happening. There's no conduction. Let's draw current. Easy. Let's first draw current, because when you draw current, then we can draw everything else. Okay? So is current going to conduct before this point? No. So current will start conducting here. Current conducting meaning what? Khalas, I don't care. This value of voltage is higher than this value of. What does the circuit look like? It looks like my source, short circuit for the diode, then R, and really just an L. Now, because I know that my DC source is higher than the AC source. Right? So it looks like the same. Looks like the same circuit like before. So what will the current look like? Exactly like before. It will actually let's do this before we go to the RL with the source case. How about we go to the let's do the R source case. Okay, R source case, no L. This is not in the text. The R source case is not in the textbook here. If we do the R source case, so how will the current look like? Before the AC source is less than the DC source, nothing will happen. Same thing, right? As soon as the AC source is greater than the DC source, current will start flowing. How will the current look like?
The source minus BBC over.
Exactly, it will be your AC source minus your DC source. Huh? This is VR. What? VR will look exactly like the current, right? Since this is a resistive circuit, then the current will look exactly like the voltage across the resistor, right? So the current will look like what? It will be the AC source minus the DC source divided by the value of resistance, right? Just the AC source value minus the DC source value divided by the value of resistance. So AC minus DC here is 0, right? So initially I have a current of 0. So before here it's 0. And then at this point it's the AC minus DC, so it's this difference divided by the value of resistor. So it's this difference scaled by the value of resistor. So how about here? The 0 as well. Right? So here, between them it looks like this. And then it's 0. And then 0 as well. Right? So only when the AC source is higher than the DC source will there be any conduction. Right? So here the DC source is less, so which means that the currents want to flip polarity. It's the AC minus DC. AC minus DC is a negative number, so the voltage is negative across the resistor, which means the current wants to be negative through the resistor, so it's going to try to force negative current through the diode, or the diode will block. Right? As soon as the current tries to go negative. So do we see the resistive case? So this is the resistive case. So how will the inductive case look like? Now I add a inductor to there. So this is R, and now L case. So what will the current look like? So this is the current for the resistive case, IR. This is IR case. Now what will the inductive case current look like? It will start at the same point, right? But will it rise as fast? No, it will not rise as fast. It will not rise as fast as the resistive case. How about where will it fall? After the resistive case. So the resistive case current fell here. This can fall here, can fall here, can fall here, can fall here, can fall anywhere. Depending on the value of inductor. Right? So let's say, let me just take one of them and draw so that we can draw the output voltage as well. Yeah. So let me just take it here, like I say here, for example. If the current stops here, what will the output voltage look like? Yeah, as long as the current is conducting, V output looks like V input. Do we agree? I mean, as long as the diode is conducting, V output looks like V input. So here, this is my V input.
So we're not including VDC?
What do you mean we're not including VDC?
Because we are-
No, it's included. All of this is V out. So all of this is V out. It's included in there. Right? So I'm not only looking at the voltage across the R and the L. I'm not going to subtract the DC from it. I'm looking at the output voltage across my load. My load was this whole combination here. So the output will look like what? Because the circuit, when the diode is conducting, the circuit looks like this. R, L, and a source. So input is equal to output. So my input will equal output as long as there's current flowing in the circuit. So, which means that, okay, current starts flowing here. So initially there is, the output is 0. And then the output looks like the input. Huh? Right? And then, right? It looks like the input. Until where? Until current stops conducting. And then goes back to 0 again. Yes? No? Okay. So these are the three cases. And the only difference between now the equation of current here is, and the equation of current that we talked about before is what? Again, I of t is going to equal what? The I forced plus I forced of t plus I natural of t. But here I have I forced due to the AC source and I forced due to the DC source. So I will show you the equations now. So the I force due to the AC source is the value of the voltage divided by the impedance. How about the value of the forced value of the current due to the DC source? It's the VDC divided by R because it's a steady state solution. There's no AC component. It's just a DC source, so it's VDC divided by R. So, and then you have the AE to the minus T over tau. So this current, the equation for current here will have the voltage divided by the impedance, the phasor form. And then it will have a DC component, and then it will have the exponential component. Any questions on the waveform? We will look at them on the slides now, and we can comment more. The one thing that is common to all of these is the fact that, of course, I'm using a diode, and hence my output voltage, I cannot control it. My circuit controls the value of my output voltage, right? This output voltage will have an average value. This average value I cannot change, right? It depends on the value of the R, the L, and the DC source, right? If I increase the value of the DC source, what's going to happen? Now I move this to the left, right? And I move the end point to the left. I move this to the right, and I move this to the left, right? If I increase the value of the DC, I'm opposing current, right? If I increase the value of the DC, I'm opposing the current caused by the AC source. So which means that this point here will start later, and this point here will fall before, right? That's what, if I increase the value of R for the same value of DC source, it will start at the same point, but if I increase R, this point will move to the left. How about if I increase the value of L? It will start at the same point, but this point will move to the right. Okay? This point we will calculate. We will have to calculate because we know its initial condition. We know the initial condition here. The initial condition here is when the VDC is equal to the Vmax sine omega t. So at this point, when the VDC of theta is equal, of which theta? Theta is the point where these two are equal to each other. We will calculate the equation. We know where this starts. It's when the DC voltage is equal to the sinusoidal voltage. But we still don't know where it stops. Where it stops will be an equation that will have a variable like the A here, but we will have to calculate from the initial condition. We will show you the equations, but first I want to go through all the waveforms. So if we're okay with the waveforms, then that's good. Then there's another set of waveforms. So are we okay with the three types of waveforms that I showed? Okay. I will review them again, but add a little bit of trick to it, okay? A little bit of, instead of having a diode, we will add a thyristor, right? So let's review the diode case, the R case by itself. So we have a diode, resistor. This is just review, okay? So if this is a review, if this is my resistor, this is my output voltage, and then what do my waveforms look like? Again, this is my input. The output voltage looks like the input all the way until pi. At this point, the current waveform tries to go negative. The diode starts blocking, which means my output voltage stops at this point, and I have 0 beyond that. What if I change this diode to a thyristor? and I provide a gate pulse to the thyristor somewhere here, what will the output voltage look like? What does a thyristor do? Thyristor means the device. Go ahead.
It turns off when you tell it to turn on.
Exactly.
Stops when it goes negative.
Stops when the current tries to go negative, right? Because as soon as you turn it on, I'm a diode. After that, it's a diode. So before that, it's an open circuit. So exactly. So if this was my output voltage in the case of the diode, the output voltage in case of the thyristor will look like 0 initially, and then as soon as the thyristor gets the gate pulse, it turns on, and the output voltage will look like the input voltage until this point. At this point, what was happening? The current tries to go negative. This thyristor is a diode now, so it will turn off wherever the diode would have turned off. Diode turns off here. Khalas, it will turn off here. So this is now my output voltage. What's the difference between this output voltage and this output voltage? I change the average value, right? So now I can control the average value. So if you have a DC motor, control the average value of DC across the motor, right? So that's the difference. So that when you add a thyristor, these thyristor, we call them semi-controlled devices, right? They are thyristor or SCR or whatever. It's a semi-controlled device. You cannot turn it off. It will turn off based on what the circuit does. Here, this is what the circuit did to it. The circuit forced it to turn off at pi. If I remove this thyristor and I put a MOSFET or a BJT or a fully controlled device, then I can turn on whenever I want to, and I can turn off whenever I want to, right? But I cannot with this thyristor. The thyristor, I finished. I turned it on. I have no way to turn it off. The circuit turns it off when current tries to go negative, right? So now I have some control features, but maybe not the best, right? Maybe not the best. Maybe it would have been okay. Forget about power electronics, okay? From a signals and systems perspective, okay? Which looks more like a sine wave, okay? Something like this, or something like this. The top one, right? So this is something I can do with a thyristor. Well, actually, I cannot do this part, but regardless. But the idea is with thyristor, I cannot turn it off, right? So I cannot turn it off. So even though I can control the voltage, but I may have a hit on my harmonics, right? The closer you look like a sine wave, the lower the higher order harmonics are that you have in your system. If you have a lot of third and fifth and seventh harmonic, these are low order harmonics. They affect the waveform shape, right? So you don't want to have any of those. If you have 20th harmonic, 21st harmonic, 25th harmonic, you don't care, because very high order harmonics, they're not going to produce current. What does current equal to? Current equals voltage divided by the impedance, right? Impedance of the inductance is equal to what? N omega L, right? N omega L. What happens to N as we have high order harmonics? N becomes very large. The impedance becomes very large. So I don't care how much voltage I have at high order harmonics, because my impedance already became big. So I have a huge impedance to high order harmonics. The problem happens when you have, in a power system, when you have low order harmonics, when you have third and fifth harmonic. The impedance is not huge. So anytime you have a voltage at that harmonic, then you have current flowing in the system at that harmonic, and you have a problem, right? So that, one disadvantage of thyristors is you cannot really, with a power converter based on thyristors or SCRs, you will not get a nice harmonic spectrum for sure. You'll get poor power quality. So you may have to add some filters later, before, but you will get a cheap converter because it's a very cheap device compared to the IGBTs or MOSFETs, and you can run a very high power converter. Remember in our first slide, first class or second class, we showed this curve where operating characteristics of different types of devices, and we saw thyristors can operate at the highest voltages and the highest currents. Right? So you can definitely build high power converters using thyristors, but the waveform quality will be poor, which means you have to add some filtering stages. Yes, sir.
You use triac, right? The triacs are bidirectional.
Sure. The triac, I'm trying to produce. This is AC to DC, right? For triacs, I'm gonna use them in chapter 5 to produce an AC as well. AC to AC. I will reduce the value of the RMS value of AC in chapter 5. But still, same thing. You cannot turn it on and off in a controlled fashion. You can only turn it on. Triacs will also turn off when it's a thyristor. At the end of the day, triac is nothing but a thyristor like this way and a thyristor the other way. Right? So if I do this, I get what? I provide a gate pulse here and a gate pulse, let's say here. What will a triac do to the output voltage? Output voltage will look like this. Then it will wait. It will be 0. And then it will look like the input for this part of the cycle as well, right? We will cover that in chapter 5. But this is here. I'm getting the output here is AC, right? If the area here is like the area here, then I have a 0 average value. I'm creating AC. I'm controlling the value of the RMS, not the average. Average value is still 0 here. In this chapter, we're talking about AC to DC. We're trying to create an average value for the waveform. Okay, so everybody's okay with this, the single thyristor case? So same thing, we'll go from thyristor now with the R circuit to RL. Okay, so first we'll review the diode case, and then we'll change it to a thyristor and see what happens. Same thing, R, L, and this is my V output. And I still have the same sinusoidal V input, and I want to draw all my waveforms again. So this is my input voltage. Again, first thing, try to think of the current. What will the current look like? For the RL case, as soon as the voltage becomes positive in this diode circuit, then the potential here becomes higher than the potential here, and the diode conducts. As soon as the diode conducts, the circuit looks like this RL circuit, RL and a source. The input, RL and a source. The current has a forced response and a natural response, but it's a linear circuit, right? What will the current look like? This is the resistive current case. And now for the inductive current, and now I have an inductor in there, so what will happen is the current will, instead of rising abruptly here, it will rise slower. And instead of falling here and becoming negative, it will always fall beyond the resistive load case. Right? Somewhere beyond. Where depends on the value of the inductance. Right? So not here, somewhere after that. Somewhere after that, the current becomes 0. Current becomes 0, what does the output voltage look like? Output voltage will look like my input voltage all the way until the current becomes 0. Right? So this is the output voltage across this circuit. Okay? Now, this is with the resistive case. How about if diode case. The shortcoming with the diode case is I cannot control the average value of this voltage. Right? It's there because of the value of R and L. How about the thyristor case? I provide a gate signal here to the thyristor. So what does the output voltage look like? Well, actually, what does the current look like first?
It only starts to rise after the signal.
Exactly, it will only start rising here. But as soon as it starts rising, what happens? The circuit looks like this. So before this, what was the value of current? 0. So before this was 0. And then at this point, it will start behaving the same way as this current. Same way as this current. Behave the same way. Because the circuit looks the same. It looks exactly the same. It will start behaving the same. So it will rise, and then it will fall after a certain amount of time, depending on the value of R and L. And at that point, beyond this point, current tries to go negative. Diode, thyristor, this is not, I mean, as soon as this thyristor turns on, it thinks it's a diode. So the diode would have turned off if the current tries to go negative, so the thyristor turns off as well. Now what does the output voltage look like in this thyristor case? So let's draw the input voltage. Input voltage. So the output voltage will look like what? Initially, 0, because I didn't provide the gate signal. And then the output will look like the input, output. It will look exactly the same. As soon as the device conducts, the input and output are exactly the same. Until when? They will look exactly the same all the way until current becomes 0. Okay? And then this point is depending, again, this point depends on the value of R and L. So it can come to the left, come to the right, whatever. So you can actually imagine a point where you can actually create a negative output voltage, right? Move this gate signal all the way to the right, provide something here. You will turn it on here, current will start rising. When will it fall? Somewhere beyond this point, later. I mean, I drew it here that looks like 0, but it depends on the value of R and L, right?
If you start the thyristor later, won't it rise to a lower?
Sure, it depends on the value of voltage. Again, of course, it will depend on the value of the voltage and the value of the R and the value of the L, right? So I cannot tell you where it will fall exactly, right? We will write the equation for current. But what is the equation for current? The equation for current will look exactly the same. Again, forced response and natural response. Forced response due to the source. Natural response due to the fact that I have an RL circuit. Right? We will look at the equation, but the equation will look exactly the same. There will be nothing different with this equation. Now we'll do the last case. The last case was RL and a source, right? RL and a source case. So we have my diode initially, R, L, and my DC source, R, L, VDC, and then I will draw the waveforms. This is my input voltage. This is my DC source. Before this point, nothing is happening in the circuit, right? The current is 0. We agree? The resistive current would have stopped here, correct? The inductive current will stop somewhere later, right? Somewhere later, whenever that is. So as soon as I have this, these 2 points defined, where I will start and where the resistive current would have stopped, then I can draw my current waveform. And then, as long as there is current, then the input voltage is equal to the output voltage. So between this point and this point, input voltage is equal to the output voltage. So just draw a dotted line here. This is your input voltage. Here, between these 2 points, this point and this point, the input is equal to the output. So the output voltage looks like this. 0 initially, this waveform, equal to the input, and then here. This will be your V output in this case. If I provide a gate signal now I convert this to a thyristor. Okay? If I provide the gate signal here, what's going to happen? Nothing will happen. Nothing will happen. It will never turn off because you provided it with a gate signal, but it thinks it's a diode. Diode will not turn on, so it will not turn on. It's not going to wait until... So you have to provide your gate signal after the point where the DC value is equal to the AC value. So you provide your gate signal, let's say here. You provide your gate signal here, finish. What does your output voltage look like? 0 initially, all the way until the gate signal. And then output voltage equal to the input voltage because the device is on. Then when does it When does output voltage become 0 again? Output voltage becomes 0 when your current stops. Assuming the current stops at the same place, then you will get this for the output. Right? So before, if you provide the gate signal before this point, it has no effect. Provided after this point, there's no change to the shape of the current, because the current will start at a certain current will start here now, right? The current waveform will not be, of course, this blue waveform. Current will start here, it will rise here, and then I assumed here it just falls at the same place, so maybe I just change the value of R and L. It may change, it may fall before, maybe fall after. Depends on the value of R and L, right? So for the same value of R and L, I believe it will fall afterwards, right? So you do the simulation for the same value and add a thyristor instead of the DC source, and you see where it will fall. Okay? So the waveforms, so the advantage between what we did here with the thyristor versus the diode is now I can control the average value. Can I increase the average value? No, I can just decrease. Right? I'm only removing parts of the waveform. Right? I'm removing area. I'm not adding area. Right? So these are all step-down converters. So typically, you will have, let's say you want a motor to run between 0 and 100 RPM. 100 RPM will have to correspond to your highest voltage. Right? So, because these converters will step down the voltage. So you will typically have to make sure that you are satisfying your maximum voltage condition first. So these are all stepping down the average value. They're not stepping it up. They cannot step up the average value. So any questions on the three cases with diode or with thyristor? Now this is the whole chapter. So the only thing now we will do is look at the equations. So we did the whole chapter. Right? Actually, there's one small thing left at the end of the chapter we'll do next time. But so next time, I can stop here. Actually. So we went through the diode R case, the RL case, and then the RL with a source case. They do some piece-by simulation. The RL with a source case with the diode, and then I missed this one. There's a freewheeling diode. Next time we'll do this one. So there's a special case called with a freewheeling diode. We'll go over that next time. But then we do the what? Then there's there's two special cases. There's still stuff to do here. So I didn't finish the chapter, unfortunately. But then they do this. They do the thyristor with a resistive load, thyristor with a RL load, thyristor with a RL and a source. Right? So we did a lot of the chapter, but we still have a few things to cover in the chapter, and as well as the equations. So hopefully the waveforms you feel comfortable with, try to draw them. Draw with your hand. Then draw the waveforms with your hand. It will help you. So we'll stop here. If you have any questions, let me know. Any questions?